In this lesson, we're going to take a look at velocity time graphs. Now, we've looked at position time graphs, and we know how they show how objects' position changes in time. But a velocity time graph shows how velocity changes in time. And there's a couple major differences we need to pay attention to when we're looking at this graph. The first is that it's showing different information, right? It is not showing where an object is. Velocity is speed with direction. So a velocity time graph is showing how fast an object is moving and which direction it's moving. So you'll notice right away that on a velocity time graph, we actually do go into the negative region. I have zero velocity in the middle, and then I'm going to have -1, -2, -3, and this is in meters per second, because when we have a negative velocity, all that negative is indicating is that the motion is back towards the reference point. I'm going to go ahead and label that on this graph. So towards the reference point, because we always move in front of the reference point, but we can move away from it or we can move towards it. And so positive velocity is away from the reference point. And again, we could have 1, 2, 3, 4, whatever meters per second. Now, for now, we're only going to look at velocity time graphs that have horizontal lines. And these horizontal lines are different than the horizontal lines that appear on a position time graph. On a position time graph, a horizontal line meant we're in the same position. That position never changes, and so we're not moving. But on a velocity time graph, this horizontal line says, I have a constant velocity. It's not a constant position, it's a constant velocity. So this section of this graph for those 2 seconds shows that this thing is moving at a speed of 3 meters per second in a positive direction. That means it's moving away at 3 meters per second. If it were to drop down and come like this for a couple more seconds, then what we would see is that it's still moving away, but it's doing it at a slower rate. It's moving away at 1 meter per second for those 2 seconds. If it drops even further and comes down, say, to -2 meters per second for a couple seconds, then that still says that the object is moving. It's just moving towards the reference point, right? This is a negative velocity. So all of these horizontal motions are not at rest. They're all constant velocities. So when we break this graph down into intervals and we analyze its motion, we would say, all right, from 0 to 2 seconds, this object moved at 3 meters per second. So the velocity is 3 meters per second. From 2 to 4 seconds, the velocity is 1 meter per second. And from 4 to 6 seconds, the velocity is -2 meters per second. Now, what about rest? Can I have a velocity time graph that shows rest or no motion? Well, sure. If this line then popped up here and stayed at 0 for a little bit, that would be rest. So the only time we have rest is if there's actually 0 velocity. So 0 velocity means the object is at rest or is not moving. If it's not at 0, it is moving, right? If it's positive velocity, it's moving away. If it's negative velocity, it is moving towards the reference point. And because we know the equation that relates velocity, displacement, and time, we can actually do a little bit of math and figure out how far an object has moved. So in those first 2 seconds, if it's got a time of 2 seconds and a velocity of 3 meters per second, remember delta x is velocity times time, we can take our 3 meters per second times our 2 second interval and say that it moved 6 meters, and it's positive 6 meters. It was moving away 6 meters. From 2 to 4 seconds, that's another 2 second interval. We can say that the change in position is 1 meter per second times 2 seconds. That's 2 meters that it moved away. And then during this last 2 second interval, 4 to 6 seconds, our change in position would be -2 times those 2 seconds, which is -4 meters, which means it's moving towards, right? So velocity includes direction, so it's positive or negative, and the horizontal line shows a constant velocity. Later we'll see sloping lines which show changing velocity, but for now we're just going to look at these constant velocities. Now, we found displacement, but we can't find actual position, because if I started, let's say I have my number line here, my reference points here. If I started at 2 meters in front of the detector and I moved 6 meters away, right, 3, 4, 5, 6, 7, 8 meters, I would have gone from here to here. And then if I moved 2 meters further away, I'd have gone from there to there. And then if I moved 4 meters towards the reference point, I'd come all the way back to here. That motion follows that, right? I moved 6 meters away, then I moved 2 meters away, then I moved 4 meters back towards my reference point. But that same exact motion could have happened if I'd have said, okay, well, let's start at 1 meter and go to 7 meters and then go to 9 meters and then come back to 5 meters, right? So this whole thing was shifted left. It still followed those displacements, but at every point in time, this would be at a different position. So a position time graph tells me where an object is, and from that, I can derive its velocity. But a velocity time graph shows me how fast and what direction an object is moving. From that, I can get its displacement, but I cannot get its position because I don't know where it started. If I know where it starts, then I can figure out where it's going to be. But since I don't know where it started, I don't know where it's at, just how far it's moved.